Hello there, and welcome to Science for Sleep, where curiosity gets cosy and science tucks itself gently into your thoughts like a soft blanket at the end of a long day. Tonight, we're drifting towards something that sounds like it belongs in the heart of a sci-fi novel, or hidden deep inside a laboratory beneath a mountain. It's invisible, rare, and if you met it under the wrong conditions, it could unmake you in a blink. Antimatter. Not just the stuff of comic books or particle colliders, but a real, measurable, magnificent part of our universe, and perhaps the most dangerous substance in existence. Dangerous not because it's out to get us, but because it is perfectly opposite. And in that oppositeness it holds the power to erase. But don't worry, we won't be exploding any atoms tonight. Just thoughts. Gently. So tell me, where are you tonight? Are you under stars or under a blanket? What time is it in your quiet little corner of the world? If you find yourself unwinding here, if this curious quiet brings you calm, I'd be grateful if you tapped like, maybe subscribed. It helps this sleepy little science nook find its way to others who could use a soft place to land. So settle in, let your thoughts slow like dust in moonlight, and let's begin. Because somewhere between the spark of creation and the silence of space lies a question too big to ignore. What is antimatter, really? Imagine this. You're holding a smooth black pebble in your hand, cool to the touch, perfectly round, silent. It looks just like any other stone you might find on a quiet beach. But this one, if it were antimatter, could erase a city. That might sound dramatic, and it is, but it's also true. Tonight we're not rushing to the equations, we're pausing here in the feeling. Because before we understand what antimatter is, we need to understand what it feels like to think about it, and what it does to our imagination. Because antimatter isn't something we see, it's something we sense the edges of, like a whisper of danger in an otherwise quiet room. Like shadow, not in the scary sense, but in the deeply opposite sense. Antimatter is a reflection, a twin, but not one that follows your lead, one that vanishes the moment you meet its gaze. In dreams and nightmares alike, we often encounter doubles, mirror worlds, evil twins. It's a psychological motif that shows up in folklore, myths, and yes, science fiction. But maybe it's not so fictional after all, because even in the waking world, opposites define us. Matter and antimatter, left and right, up and down, self and shadow. What makes antimatter unsettling isn't just its power, it's the feeling that something could exist that looks just like you, but isn't. A version of the universe that almost is, but not quite. And that closeness to familiarity, that unsettling mirror is what grips us. We don't dream of antimatter the way we dream of stars or forests or oceans. It doesn't feel organic. It doesn't feel old. It feels engineered, surgical, like an answer whispered by a machine that knows more than we do. So maybe the question isn't what is antimatter. Maybe it's why do we find it so strange? Because when you hold a pebble in your hand, you know it's not going to blink out of existence. But if that pebble were antimatter, one atom of it meeting its ordinary twin in the air, it would unleash pure energy. No fire, no smoke, just gone. So what does it mean then to know that you live in a universe where such things exist? It means we live in a place of delicate balances, where opposites exist but rarely meet. And when they do, they erase each other perfectly, without residue, without a trace, like a memory you can't be sure was ever yours. That in itself is a kind of poetry, because if antimatter is terrifying, it is also elegant, the most precise thing we've ever found. And that idea that the universe is not just matter, but its perfect negation, is both haunting and, strangely, calming, like a puzzle piece that confirms the puzzle is real. So before we talk about the science of it, the particles, the charges, the collisions, just sit with that idea, that you are made of matter, but for everything that exists, something could have been made that isn't. A world that could have formed, but didn't. And that the reason you exist at all might just be because somewhere, a tiny bit more matter survived the meeting. In ancient stories, danger often had a name. Leviathan, chaos, the underworld. These were not just stories to scare children. They were attempts to explain the inexplicable. Why things disappear. Why balance matters. Why the world feels sometimes like it's holding its breath. Antimatter may not come with horns or a flaming sword, but it does what many of those ancient creatures did. It undoes. Perfectly. Elegantly. No thunder. Just symmetry. The ancient Greeks didn't know about positrons or antiprotons, but they knew that nature tends toward balance, that opposites define meaning. Fire and water, air and earth, light and darkness. In Hindu cosmology, the universe is destroyed and reborn again and again in cycles. Creation and destruction, bound together like breath in and breath out. In Taoism, yin and yang are not enemies but complementary forces. In perfect balance they make the world whole. And perhaps that is the truest metaphor for antimatter. Not a villain, not a poison, but a partner. A dancer who steps precisely opposite, so that the dance itself can go on. It's only when antimatter meets matter that danger arises. And perhaps that is the real myth here, that two perfectly matched things cannot exist in the same place without undoing each other. The opposites, while necessary, must remain apart. In some ancient Egyptian texts, the afterlife is not a place of punishment, but of careful symmetry. Your heart is weighed against a feather. Not because the feather is powerful, but because balance is sacred. In that way, antimatter is almost spiritual. It reminds us of the razor-thin margins of reality, that for every step forward, there might be a backward echo, and that sometimes, even in the cold world of physics, the rules are written in paradoxes. So no, antimatter doesn't appear in mythology as a named force, but its essence, its symmetry, its peril, its beauty, has always been there, in rituals, in balance, in the knowing that not everything must be visible to be real. And so we begin to understand not just what antimatter is, but what it means. It means that nature is more symmetrical than we ever imagined. And yet, somewhere, the symmetry broke. Because if matter and antimatter were created in equal parts, as physics tells us they should have been, then where is all the antimatter now? Why are we here, and not erased? That's the mystery we'll begin to explore next. We now know what antimatter feels like: unsettling, poetic, potent, and we've traced how ancient cultures might have unknowingly gestured toward its deeper symbolism. But now, gently, let's ask, what is it? In the quietest sense, antimatter is just matter's twin, its perfect opposite, not in shape or substance, but in charge. Let's take the electron, a tiny negatively charged particle that lives in every atom of you. Its twin is the positron, same mass, same spin, same fundamental nature, but its charge is positive. That's it. That's the difference. One leans left, one leans right. Otherwise, they're mirrors. It's this delicate difference that makes all the difference. Because when matter and antimatter meet, a positron and an electron, say, they don't fight, they don't push, they vanish, converting every last ounce of their mass into pure energy. Einstein told us this was possible. E, mc bstu. Mass and energy are two sides of the same coin, so when a particle and its antiparticle meet, the coin flips, and what was once solid disappears into a flash of photons, light, bright, final. This process is called annihilation. A word that sounds violent but is really just precise. Clean. Nothing is left. It works both ways too. Sometimes a high-energy photon can become a pair, an electron and a positron summoned from pure light, creation and destruction dancing as they always do. So, antimatter exists. We've seen it. We've made it. And yet, it's gone. Gone from the universe mostly, gone from our streets, our clouds, our skin. If antimatter had been made in equal measure to matter, then every atom in your body should have an opposite number. But if it did, you wouldn't be here to wonder about it. That mystery has a name: the baryon asymmetry problem. At the beginning of the universe, in the moments after the Big Bang, matter and antimatter should have been created in equal amounts. Perfect symmetry, equal and opposite. So they should have annihilated each other entirely. Flash. Gone. The universe reduced to light. No stars, no planets, no tea, no dreams, no lovers holding hands in the dark. And yet, here we are, which means something tipped the scales. Some tiny imbalance, a sliver of extra matter per billion particles, somehow survived. Why? We don't know. Not fully. Some theories speak of CP violation, a crack in the symmetry of nature that means the universe slightly favours matter over antimatter. Others suggest deeper mechanisms we haven't uncovered yet, but no one has solved it. Not yet. It remains one of the greatest unsolved questions in physics, the question of why anything exists at all. And all of it, you, me, this sentence, the night air slipping through your window, may owe its existence to the tiniest twist in that mirror. Let's go deeper, not into the equations, but into the edges. Antimatter isn't just theoretical, we create it, often unintentionally. Cosmic rays striking the upper atmosphere can produce positrons. Certain kinds of radioactive decay release antineutrinos. Hospitals use it every day. PET scans, positron emission tomography, inject tiny amounts of a radioactive substance that emits positrons. These annihilate with electrons in the body, producing gamma rays that can be mapped to create detailed images of the brain. Your thoughts, your memories, your dreams, lit up by the ghost of antimatter. We also make antimatter deliberately. Particle accelerators like those at CERN can generate antiprotons, trapping them in magnetic fields. We can hold them for brief moments, study them, ask them questions, but not many, and not for long, because antimatter is hard to keep. It wants to disappear, or rather it wants to meet matter, and that meeting is always a goodbye. So we build traps, magnetic cages, isolation chambers. We treat antimatter like a rare animal, wild, powerful, and prone to vanishing. All this effort for just a few atoms, just enough to measure, just enough to know they're real. And if we had more, just a gram of antimatter would release the energy of a nuclear bomb. Not because it's more dangerous than matter, but because of how perfectly it turns mass into energy. No waste, no residue, just the math of the cosmos played in reverse. This too is a paradox. The rarest, hardest to make substance in the universe is also the most energetic, the most efficient, the most elegant. So we chase it, not to destroy, but to understand. And maybe, one day, to use. For propulsion, for medicine, for unlocking deeper truths about why there is something rather than nothing. Because antimatter is more than a danger, it is a reminder that for everything that is, there might be a thing that isn't, and that in every shadow there is a trace of light. Long before particles had names, long before the word antimatter was ever imagined, we told stories about balance, about mirrors, about twins. The human mind, it seems, has always been drawn to symmetry, and in the absence of particle physics we used myth. In Zoroastrianism, one of the oldest known organised religions, the world is a battleground between two primal forces, Ahura Mazda, the force of order and light, and Angra Mainyu, the spirit of chaos and darkness. Neither is evil in the simple sense, but they are perfect opposites. Their eternal struggle defines the shape of reality. In ancient Egyptian mythology, Maat represented harmony, truth, and balance, while Isfet symbolised disorder and unmaking. The afterlife depended on whether your heart, your essence, was in balance. Symmetry wasn't just aesthetic, it was moral, cosmic. These myths weren't science, but they echoed something fundamental. The universe feels like it runs on pairs, on opposites. In Norse mythology, fire and ice shape the cosmos. In Chinese tradition, yin and yang spin the world into being. And across countless cultures, the idea that every force has its counterforce, its partner, its rival, is as old as language. Even in storytelling, we see this mirrored structure. Heroes and nemeses, light sides and dark sides, reflections of one another, bound in tension. So when scientists finally discovered antimatter, it felt both utterly alien and strangely familiar, as though physics had confirmed a hunch humanity had carried all along. For everything that exists, something equal and opposite might be out there too. The name antimatter didn't arise until the 20th century, but the seeds were planted in the late 1800s as scientists began to explore the structure of the atom. J.J. Thomson discovered the electron in 1897. It was the first subatomic particle known to science. Then, in 1928, a young physicist named Paul Dirac proposed a strange and beautiful equation. It was an attempt to unify quantum mechanics and special relativity, two pillars of modern physics that didn't quite get along. But what Dirac found was more than a bridge. He found a shadow. His equation worked, but only if electrons had a counterpart, a mirror twin, identical in mass but with opposite charge. At first this seemed absurd. No such particle had ever been observed. Some physicists thought it was a mathematical quirk, a mistake, but the universe doesn't make mistakes, it makes symmetry. In 1932, Carl Anderson, working with a cloud chamber and cosmic rays, discovered something astonishing. A particle, just like an electron, but positively charged. A positron, the first confirmed piece of antimatter. Dirac had been right. The mirror was real. From there, the idea spread. If electrons had antiparticles, so might protons, neutrons, entire atoms of antimatter. And so they were found, slowly, carefully, piece by piece. As the idea matured, so too did its mythos. Science fiction quickly seized on antimatter as a symbol of both power and peril. In Star Trek, antimatter powers starships. In Angels and Demons, it becomes a weapon. And in the public imagination, it became a kind of futuristic magic, a whisper from the cutting edge. But outside of fiction, it remained elusive. Real, but rare. Confirmed, but not conquered. Still, the story was irresistible. Imagine an entire universe made of antimatter, galaxies with anti-stars, planets with anti-oceans, beings made not of flesh and carbon, but of positrons and antiprotons. Could such a place exist? Would it be any different? Or would it look just like ours, until the two touched? That idea lingered not only in science fiction, but in scientific debate. Because the laws of physics allow it. Antimatter obeys the same rules. If it had been favoured in those first cosmic moments, it might be us looking out into the stars, wondering if somewhere matter exists. Even in culture, antimatter began to take on a symbolic life. It became shorthand for opposites, for forbidden matches, for perfect, fatal intimacy. You see this in poetry, in cinema, in relationships where two people burn too brightly when they meet. Because the metaphor is too beautiful to ignore. Antimatter isn't just the opposite, it's the perfect opposite. Not flawed, not incomplete, just inverse. And when it touches the thing it mirrors, the result is not conflict, it's obliteration, which, depending on your perspective, is either terrifying or transcendently pure. And so even as science advanced, as cloud chambers gave way to accelerators and theories to technologies, antimatter remained, culturally, a mystery, a riddle half solved. Not just a physical phenomenon, but a story we'd been telling for centuries without realizing it. Not just a particle, but an idea. What makes antimatter so haunting is not just its rarity, but its absence. The sense that it should be here, more present, more balanced. But it isn't. Where did it go? Was it ever here at all? Cultures have always had stories of the lost half, the shadow twin, the thing that was taken. From Plato's tale of souls once split in two, searching for their missing half, to mirrored worlds in Hindu cosmology, where every action here echoes in a subtler realm, to the ancient Jewish myth of the golem, a double made from earth, animated but not quite human. These aren't tales of science, but they are tales of reflection, of the not quite, the nearly real, the thing that is the same, but not. Antimatter feels like it belongs in that lineage, a discovery not just of physics, but of myth fulfilled. The idea that something can exist only in the absence of its twin, that the mirror is real but cannot be held. So in that sense, the discovery of antimatter wasn't new. It was ancient. We just hadn't known its name. In the decades following Dirac and Anderson, antimatter began to step out of the shadows of myth and into the bright, humming laboratories of high-energy physics. It wasn't easy. The particles were fragile, fleeting, the collisions brief and rare. But still, the work went on. By the 1950s, physicists had created antiprotons, the antimatter twins of protons. These weren't just theoretical anymore. They were observed, trapped, studied. For the first time, scientists held pieces of a mirror universe in their hands, and then, slowly, they began to build. In 1995, scientists at CERN announced something that once would have sounded like science fiction. They had made antihydrogen, a positron, an antiproton, bound together to form the simplest possible atom of antimatter. For the first time, antimatter wasn't just a particle. It was an element, something that, at least for a moment, could have been part of a world. But it didn't last. It couldn't. The moment it touched ordinary matter, it vanished. Still, it proved what was possible, not just in theory, but in practice. In the years since, scientists have trapped antimatter atoms for longer, measured their spectra, compared their behaviour to matter. So far, the mirror holds. Antimatter behaves just like matter in almost every way, except one. The universe prefers matter. We don't know why, not yet. But we are trying to find out. That search continues today, not just in labs, but in the skies. Satellites scan for cosmic rays that might hint at regions of antimatter. Detectors look for gamma-ray bursts from annihilation events. Some researchers have proposed that pockets of antimatter could still exist, isolated, distant, invisible to our ordinary tools. Perhaps there are anti-stars hidden in the dark. Perhaps there are clues in the background radiation, or in the behaviour of neutrinos, or in the quiet hum of deep space. So far, nothing definitive. But the search continues, because the implications are vast. If antimatter can be found, if its asymmetry can be explained, we might not only understand our own existence more deeply, we might also rewrite the future. Today, the story of antimatter touches more than science. It inspires art and architecture. You can find murals of Dirac's equation in university halls, see antimatter symbolised in sculpture and song. Artists love its symmetry, its danger, its purity. Philosophers love its implications. Is reality only real in the presence of its opposite? Can something be defined without its negation? Does the presence of antimatter hint at deeper truths about duality, about perception, about the limits of knowing? We look into the mirror of physics and see not just equations, but ourselves, and that too has precedent. In ancient Japanese philosophy, the concept of ma refers to the space between things, not the thing itself, but the absence that gives it form, the silence that gives meaning to sound. Antimatter, in a sense, is a kind of cosmic ma, not the presence of energy, but the echo, not substance, but potential, the shadow that lets us see the light. As we close this chapter of our exploration, we find ourselves walking backward into the future, carrying ancient ideas, seeing them reborn in modern laboratories, remembering that even the most cutting-edge discoveries often feel familiar. We've always known about opposites, about mirrors, about the strange magnetism of that which almost is but isn't. We gave it new names: positrons, antiprotons, annihilation. But the story was always there. A universe defined by tension, balanced on the edge of a vanished twin. And every step we take to understand antimatter is also a step into understanding ourselves, our myths, our metaphors, and the invisible structures that hold them together. So the next time you hear the word antimatter, perhaps don't think first of destruction. Think of symmetry. Think of ancient echoes in modern halls. And think of how quietly the universe tells its secrets when we know how to listen. If you're still with me, eyes soft, breath slow, mind adrift between waking and wondering, it's time to gently turn the page, from myth and metaphor into something more precise, not harsher, just clearer. The way moonlight can trace the edge of a leaf, even in the dark. So let's ask again, what is antimatter? Not just how it feels, not just what it symbolises, but what, in the deepest language of physics, it is. At the simplest level, antimatter is the mirror image of matter. Each fundamental particle in our universe, electrons, protons, neutrons, has a corresponding antiparticle, same mass, same spin, but opposite charge. An electron is negatively charged. Its twin, the positron, is positive. A proton is positive. Its twin, the antiproton, is negative. Even neutral particles like neutrons have antiparticles, with differences buried in their internal structures. These opposites aren't cosmetic, they're foundational. They're written into the equations that describe our universe. Quantum field theory, one of the most accurate and predictive frameworks we have, tells us that particles are excitations in fields that fill all of space. Electrons are waves in the electron field, quarks in the quark field, and so on. And embedded in those equations, quietly, inevitably, are the antiparticles. Dirac didn't invent them. He discovered that if our universe is built from these fields, then symmetry demands both matter and antimatter. It isn't a choice, it's a requirement. But this requirement comes with a rule. When matter and antimatter meet, they annihilate. Not violently, though it is energetic. They simply vanish, not into nothing, but into light, into pure energy. This is not like two things breaking. It's more like two waves cancelling each other out. The energy remains, but the form does not. And here's where the laws of physics become almost poetic, that annihilation is total. There is no ash, no wreckage. The two particles simply give up their mass, their form, and become something else. Photons, light. It's worth pausing here. Because this is a kind of magic that really happens. In particle accelerators, in distant galaxies, in the quiet interactions of cosmic rays in our upper atmosphere. All around us, tiny flashes of annihilation are happening, not enough to harm us, but enough to remind us that the universe is always in motion, always in conversation with itself, and from that conversation, we learn. Let's break it down a little more. Start with the positron, the first antiparticle ever discovered. It behaves just like an electron. It has the same mass. It moves in the same way. It follows the same rules, but it curves in the opposite direction in a magnetic field. That single difference, charge, is enough to distinguish it, and yet it's enough to make all the difference. When a positron meets an electron, they annihilate. The result is two gamma-ray photons flying off in opposite directions, carrying away the energy of the mass. And that process isn't rare. It happens inside your body. In medical imaging, positron emission tomography, or PET scans, use positron-emitting isotopes injected into the bloodstream. These isotopes decay, releasing positrons, which annihilate with electrons in your body. The gamma rays that emerge are captured and turned into images. You can see the brain think, the heart beat, all thanks to antimatter. And that's one of the paradoxes of this strange twin substance. It is the most dangerous thing we know, and the most delicate. It can light up a starship or a neuron. It can erase a city or reveal a memory. It all depends on the context, on the quantity, on the care. Then there's the antiproton. Discovered in 1955 by Emilio Segre and Owen Chamberlain, the antiproton is the antimatter counterpart to the proton. Same mass, opposite charge. It completes the trio that allows us to imagine antimatter atoms. A positron, an antiproton, maybe an antineutron. Put them together and you get antihydrogen, the simplest atom of antimatter, and we have made it. At CERN in 1995, scientists combined positrons and antiprotons to produce the first atoms of antihydrogen. They floated briefly in magnetic traps, because they could not touch the walls of their container. The moment they did, they would annihilate. And yet for that moment, they were real. Not just particles, but atoms. And that matters, because it means antimatter isn't just a mathematical trick, it can form structure. It can be shaped into something that could, in theory, build a world. One entirely unlike ours, yet exactly the same. Imagine an anti-Earth, where anti-water flows past anti-trees, where anti-cats stretch on windowsills made of anti-hydrogen and anti-carbon. The laws of physics say it would work, it would hold together. The same chemistry, just reversed in charge. The only rule is, it must remain separate, because if it touched our matter, even a little bit, the story would end. That's what makes antimatter so strange. It isn't dangerous because it wants to be. It's dangerous because it is too perfect. It meets its opposite, and together they unmake each other completely. This isn't war, it's closure, and it raises questions. If the laws of physics demand symmetry, if every particle must have its mirror, then why does our universe look like this? Why is everything made of matter? In those first moments after the Big Bang, matter and antimatter should have been created in equal amounts. Yet here we are, with galaxies and stars and you and me, and hardly a trace of antimatter left. Why? That question haunts physics. The most likely answer lies in a phenomenon called CP violation, charge parity violation. In simple terms, the laws of physics are supposed to be the same if you flip the charges, C, and reflect the system in a mirror, P. But in certain rare cases they're not. Some particles decay in ways that slightly favour matter over antimatter. Tiny differences. Fractions of fractions. But over cosmic timescales they could have made all the difference. Experiments with kaons and B mesons have shown hints of this asymmetry. Enough to prove it exists, but not enough to fully explain why matter won. So we keep searching. For better measurements. For deeper theories. For the place where the mirror cracked. Because if we find it, we might also find the origin of existence itself. And this, perhaps, is the quiet triumph of antimatter. Not just that it exists, not just that we can trap it, or image the brain with it, or build theories around it, but that it questions us. It refuses to let us rest in the comfort of a one-sided universe. It whispers that every story has another side, that for everything we understand there is something equally true, but inverted. Antimatter is not an enemy. It's not even a mystery. It's an invitation to think deeper, to look again, to ask always what might lie just on the other side of the mirror. And if you're still with me, maybe you're wondering what else antimatter can do, how it behaves, what strange properties it has when gathered, accelerated, or slowed. So let's turn the page again and follow this twin a little further. There's more to explore. Let's linger a while in the laboratory. Antimatter is more than a concept now. It's a visitor, rare, delicate, and heavily supervised. To work with it, we need patience and fields, magnetic fields to be precise, because antimatter cannot touch the walls of its cage, not even gently. The moment it does, it disappears. So physicists create traps. They shape invisible fields into bottles, gently coaxing antimatter to float, to hover, to stay. These are called penning traps and pull traps, and their designs are as elegant as clockwork. A single antiproton might circle for hours, held in place by the whisper of magnetism. Not because it wants to stay, but because we insist. In 2011, scientists at CERN managed to trap antihydrogen atoms for over 15 minutes. That might not sound like much, but in the world of high-energy physics it was a lifetime. Enough time to study, to watch, to ask questions. Is gravity the same for antimatter? Does it fall the same way? Does it feel weight? That question, remarkably, is still open. Some theories suggest antimatter might behave differently in a gravitational field. Others say no, it must fall just like matter. Experiments like Alpha G at CERN are now testing this directly, dropping antihydrogen in a controlled environment, measuring its motion. Because even though gravity seems so simple, apples, Earth, falling, its interplay with quantum particles remains mysterious. What if antimatter is the key to that mystery? Then there's antimatter and time. The equations of physics are, for the most part, time-symmetric. They don't care if time moves forward or backward. The math works both ways, but we live in a world where time flows forward. Eggs break. Trees fall, coffee cools. So where does that asymmetry come from? Antimatter might offer a clue. There's a strange idea in theoretical physics that antimatter may, in some sense, be matter moving backward through time. This isn't science fiction. It arises naturally from Feynman diagrams, the visual tools physicists use to represent particle interactions. In those diagrams, an antiparticle can be drawn as a normal particle moving in reverse. It's a mathematical shorthand. But it suggests something deeper, that antimatter might be tied to the very direction of time itself, that when you reverse charge and mirror the system, time also inverts. And perhaps the arrow of time, the reason we remember the past but not the future, is quietly written into the behaviour of these twin particles. It's not settled, but it's beautiful. Because once again, antimatter becomes more than physics. It becomes a way to ask deeper questions. Now let's talk energy. Antimatter is the most energy-dense substance we know. When a gram of antimatter meets a gram of matter, the result is nearly 2 megatons of explosive energy. That's the yield of a hydrogen bomb packed into a sugar cube. No other reaction converts mass to energy so efficiently. Fusion, the process that powers the sun, is about 0.7% efficient. Matter-antimatter annihilation, 100%. This isn't speculative. It's tested, observed, predicted down to many decimal places. That's why science fiction loves it. Not just for the drama, but for the math. Antimatter is realistic science fiction. The kind that whispers, not yet, instead of never. So could we use it? In principle, yes. Antimatter propulsion has been proposed for deep space travel. A spacecraft could store antimatter in magnetic bottles, release it in tiny amounts to collide with matter, and direct the resulting energy as thrust. Such a ship could reach a significant fraction of light speed, and that in turn opens doors to interstellar journeys, not in centuries, but in decades. The challenges are immense. We can only make picograms of antimatter at enormous cost. Storing it is hard. Containing it is harder. But the physics is sound, which means the rest is engineering. Then there's medicine. Beyond PET scans, researchers are exploring antimatter for cancer treatment. Antiproton therapy, like proton therapy, could target tumours with high precision. The difference? When antiprotons stop, they annihilate. That burst of energy could make them even more effective at destroying cancer cells, while sparing healthy tissue. Early experiments are promising, but it's still experimental, still rare. Still, it's another reminder that antimatter isn't just about destruction. It's about focus, precision, the ability to unmake, not wildly, but exactly. Like a surgeon's scalpel made of math and symmetry. Let's look smaller now. At the quantum scale, particles behave like waves. and antimatter follows all the same quantum rules. It can be entangled like any particle. It can interfere with itself. It can exist in superposition, being in some sense many places at once. This means antimatter isn't just a curiosity, it's part of quantum theory, part of the machinery behind everything. In quantum electrodynamics, QED, one of the most successful theories ever created, calculations routinely include virtual antiparticles, not just real ones flying through space, but ghostly mathematical ones that flicker in and out of existence in the vacuum. Loops in equations, echoes in the math. They're not imaginary, they're required for the theory to match experiments. In this way, antimatter is not the exception. It is woven into the rules. Even when it isn't seen, it's felt, like the shadow behind the light. And yet, for all this symmetry, something is broken. Because again we return to the mystery. Where did all the antimatter go? We should see it in the cosmos, in the stars, in the space between, but we don't. Satellites like Pamela and AM02 search for signs of antinuclei, helium, carbon, even anti-iron. If a region of space contained antimatter, we might see the products of matter-antimatter collisions along its edges. A glow, a fingerprint. So far, nothing definitive. Which brings us back to CP violation, to the subtle asymmetries, to the near misses in the mirror, to the idea that perhaps the laws of physics do not treat matter and antimatter the same. Just a little, just enough. And so we continue. Not because we're lost, but because the path is fascinating. Antimatter is real. It is here. It is part of your body, your brain, your breath. It dances in the atmosphere, rides in from space, reveals the beating of hearts. It is not the enemy. It is the partner in a dance we barely understand. A partner that steps just out of reach every time we try to grasp it. But perhaps that is what makes it beautiful. And still, there is more. How does antimatter behave under pressure? In fields beyond Earth? In the cold dark of interstellar space? How does it fit into the larger story of the Big Bang, of dark matter, of what it means to be made of anything at all? Let's keep walking. There is always another layer. So now we arrive at the edge of what we know and the doorway to what we don't. Because if antimatter has taught us anything, it's that the universe is comfortable with contradiction, with symmetry and its breaking, with particles that cancel each other so perfectly that even their absence tells us something important. Let's talk about antimatter in the early universe. In the first few microseconds after the Big Bang, energy condensed into matter and antimatter in almost perfect pairs. Imagine a cosmic dance floor filled with partners spinning out from nothing. But something disrupted the balance. Out of every billion matter-antimatter pairs, one extra particle of matter was left standing when the music stopped. And that single particle, multiplied by the sheer number of early collisions, is what makes up everything we see today. Stars, planets, you, me, all of it built from leftovers. This imbalance, the slight overproduction of matter, is still not fully understood. But it may hold the key to understanding why the universe exists in its present form. Experiments like those at Fermilab, CERN, and Japan's SuperKEK are hunting for more clues, measuring tiny asymmetries in particle decays, searching for patterns that could explain the crack in the mirror. It's slow work, but it's work that matters. Because if we find the reason, we may find the rule behind all rules, the thread that connects the quantum world with the cosmic, the answer to why something, not nothing, fills the void. There's another place where antimatter might hold secrets. Dark matter. We know dark matter exists. Galaxies rotate too fast for their visible mass. Gravity bends in ways that suggest something unseen is at work. But what it is, we don't know. Some theories suggest that dark matter might be made from particles in a mirror sector, a kind of hidden reflection of our universe, complete with mirror matter, mirror atoms, perhaps even mirror life. Could this mirror sector contain mirror antimatter? The idea is speculative, yes, but not absurd. If the early universe did produce multiple sectors, if symmetry extends deeper than we know, then perhaps antimatter didn't vanish. It merely moved into another fold, another layer of the cosmic fabric. And if so, detecting it would be difficult. Its particles wouldn't interact with ours except through gravity. But it might explain the strange silent pull we see in the stars, and once again, antimatter would become a guide, not just to what is, but to what could be. In some theoretical models, the universe could have regions, vast pockets, dominated by antimatter. Entire galaxies made of anti-stars. Perhaps even an anti-galaxy somewhere far beyond the reach of our telescopes. Why haven't we seen them? If they exist, their boundaries would be perilous. Where matter and antimatter galaxies brush against each other, we'd expect to see bursts of gamma radiation from annihilation events. But space is vast. These regions could be separated by enormous distances, too far for their edges to touch, too far for their light to reach us clearly. So we keep looking. Some studies scan the cosmic microwave background, the afterglow of the Big Bang, for irregularities that might suggest matter-antimatter domains. So far it's all tantalizing silence. But not every silence is empty. Some are just waiting for the right ear to listen. At the intersection of antimatter and gravity lies one of our boldest questions. How does antimatter fall? It sounds simple. But measuring the gravitational behaviour of antimatter is difficult. You need to produce it, trap it, and observe its free fall without it annihilating. The Alpha G and G-bar experiments at CERN aim to answer this question. If antimatter falls differently, even slightly, it could revolutionise physics. It could hint at new forces, new symmetries, or even flaws in general relativity. Most physicists expect that antimatter falls like matter, that gravity is indifferent to charge. But the beauty of science is that we don't assume. We test. We ask. We build machines that measure the path of falling antihydrogen, like watching a single snowflake drift in a glass cathedral. If the results match our expectations, it confirms Einstein's grip on the cosmos. If they don't, then a new chapter begins. All of this, the trapping, the measuring, the wondering, reminds us of something quietly profound. We don't study antimatter because we fear it. We study it because it asks better questions than almost anything else in physics. Questions about balance, about time, about the direction of the universe. Antimatter is what happens when the universe finishes a thought and then wonders what the sentence would look like in reverse. It is not the villain, it is the alternate draft. So let's step back. We've learned that antimatter is not exotic. It's fundamental. It's as real as sunlight, as near as the positrons in your body. It can be made, contained, studied. It follows rules. It makes rules. It breaks a few too. And yet, it feels almost spiritual in its precision. The way it unbinds, the way it ends things, not messily, but completely. It is the one thing we know that can erase mass entirely, not just hide it, erase it. In that sense, it is the universe's undo function, its reset button, its whisper. You may reverse this. There are more theories, more models. Some say antimatter may have different versions, that new types of antiparticles could exist beyond the standard model. Supersymmetry, axions, sterile neutrinos, all ideas that could shift our understanding of balance. But even if none of them prove true, antimatter already gives us enough wonder to last a lifetime. It teaches us that the universe does not just build, it balances, that it does not just shine, it reflects, and that sometimes the most profound truth isn't the presence of a thing, but the silence where its twin should be. This is what antimatter shows us. Not just a mirror, but a choice. Not just destruction, but clarity. A reminder that for every structure that holds, there is a structure that would have cancelled it. and that knowing the difference may be what lets us call this place real. We've eased through definitions and experiments, metaphors and mysteries, but now let's let the lights dim just a little further. We're going deeper, not faster, not louder, just inward. Because antimatter, as strange as it sounds, doesn't sit on the edge of physics. It threads through its centre. Let's start where the fabric tightens, with how antimatter is created. Not imagined, not theorised, created. You don't need a particle collider to make antimatter. It happens naturally, in the hearts of stars, in the violent kiss of cosmic rays hitting Earth's atmosphere. Even bananas, thanks to a small amount of potassium-40 decay, emit the occasional positron. It's happening quietly all the time, but when we do want to make antimatter on purpose, we go big. Particle accelerators like the Large Hadron Collider speed up protons to near light speed and smash them together. The energy released in those collisions can materialize as particle-antiparticle pairs. Why? Because energy becomes mass. E mc2. That's not a metaphor. That's physics. If you provide enough energy in a small enough space, the vacuum of space-time responds by forming matter and antimatter, paired like dancers entering from opposite wings. You can create a proton, but only if you create an antiproton too. A perfect mirrored transaction. This is called pair production. It happens in stars, it happens in colliders. It happens when high-energy photons skim the surface of a heavy nucleus and convert into an electron and a positron. This is not fiction, it's how the cosmos works. So the universe, in its most extreme places, supernovae, quasars, black hole accretion disks, is continually producing and erasing matter and antimatter, a cosmic tide of appearance and annihilation. And that rhythm, that balance, is what lets anything exist at all. Now let's stay in that collision, because once antimatter exists, it must be handled. That's where the real complexity begins. First, separation. The moment an antiproton is born, it wants to find a proton. The universe is full of protons, so we must catch the antiproton before it collides, before it undoes the very energy that made it. We use electromagnetic fields, not to hold it like a ball, but to guide it like a current. Devices called penning traps use a combination of magnetic and electric fields to hold single particles suspended in space. No walls, no surfaces, only fields. It's delicate and fleeting, but it works. Sometimes we succeed not only in catching the antiproton, but also pairing it with a positron. Together they form antihydrogen. This is where we cross from particle physics into atomic physics, from chaos into structure. Antihydrogen behaves like hydrogen. It has the same spectral lines, the same energy levels, the same chemical potential. We are at that moment not just studying particles, we are studying alternate chemistry. Now let's talk about what happens when antimatter is accelerated. Once trapped, antiprotons can be loaded into storage rings. These circular tracks use magnetic fields to steer the particles into tight loops, keeping them moving at high speeds without touching anything solid. Why do we accelerate them? Because high-energy collisions reveal new truths. When antiprotons are smashed into targets, usually thin sheets of matter, we study the annihilation products, pions, kaons, gamma rays, all fragments of fundamental interactions. These collisions don't just test symmetry, they test the fabric of space-time itself. They let us peer into forces and particles that existed in the first moments of the universe. In these moments we study strong interactions, weak decay channels, the influence of quantum chromodynamics. But all of this only works if the antimatter behaves predictably, if it matches matter in every way except charge, and mostly it does. But every experiment, every result, carries a question folded inside. Does antimatter ever behave slightly differently? If it does, then we have found the crack in the mirror. That's the prize. Not just balance, but imbalance. The tiny, rule-breaking twist that let us win the cosmic coin toss. Now a word about storage. You can't keep antimatter in a jar, or on a shelf. It touches the world and ceases to be, so we build magnetic bottles, fields shaped like tunnels or cages, vacuum chambers colder than space, containers where the walls are not walls but force. It takes enormous infrastructure to store even a few nanograms of antimatter. As of now, we produce maybe a few nanograms per year worldwide. That's enough energy to boil a cup of tea, but only if you could use it all, which you can't, and it costs billions. So the dream of using antimatter as a fuel for spacecraft or power stations or miracles remains distant. Not impossible, just remote, like the stars. Yet antimatter matters more than its quantity, because in studying it, we refine our tools, we test our assumptions, we build machines so precise they can measure a particle's charge to 1 part in a billion. That precision feeds into medicine, into metrology, into computation. Antimatter pushes the frontier, and in pushing it, we improve everything behind us. This is how basic science works. Not always with immediate use, but with enduring insight. To study antimatter is to study the design of the universe, its balance, its memory, its unspoken preferences. It is the science of opposites, but also the science of unity. Because in the end, matter and antimatter are part of the same story, one inked in reverse. And so, even in the lab, even among machines that hum and sparkle and spin, we return to a kind of stillness. Antimatter isn't flashy, not when seen closely. It's quiet, obedient, measured. Its drama is only in what it implies. That the universe is not content with single answers. It wants contrast. And the contrast is what brings the shape into view. We've seen how antimatter is made, how it's stored, how it's tested. But what happens when we go beyond that? When we ask how antimatter behaves in places we've never been, around black holes, in early inflation, in the multiverse, that's where we'll drift next, because there are places where antimatter might still be hiding, and not just as a particle, but as a question. Let's leave the lab behind for a while. Antimatter might be born in collisions and contained in fields, but it doesn't stay there. The universe is far bigger and far stranger than any single machine. And the questions antimatter raises, they stretch beyond the magnets and glass. So what happens when we imagine antimatter out in the wild, in the corners of the cosmos where the rules grow blurry? Let's begin with black holes. In theory, if a black hole consumes antimatter, it behaves no differently than if it consumed matter. Gravity doesn't distinguish between the two. It pulls in whatever comes near. But here's where it gets interesting. If a primordial black hole, one formed not from a star, but from high densities in the early universe, were floating through a region of antimatter, it could gather antimatter mass. Its accretion disk could glow differently. Not visibly, perhaps, but in gamma radiation from constant annihilation. So some scientists have proposed scanning the sky for such signatures. Looking not just for black holes, but for anti-black holes. It's not that the hole itself is made of antimatter, it's that the matter surrounding it is. And where matter meets antimatter, even at the edges of an event horizon, we see the light. Now go bigger. The early universe was a violent place. In the seconds after the Big Bang, temperatures were high enough for constant pair production. But as the universe expanded and cooled, that balance changed. Matter and antimatter began to annihilate faster than they could form. And yet, as we know, something tipped the scale. The slight excess of matter meant that while most pairs destroyed each other, some matter survived. Now, imagine a scenario where that imbalance varied from place to place. Imagine a patchwork universe where some regions favoured matter, others antimatter. At the boundaries there would be annihilation, violent, bright. But if those domains were separated early and expanded quickly, they could survive without touching. Entire antimatter galaxies could exist beyond our visible horizon. Would they form stars? Would those stars shine the same way? Yes. Photons don't care where they came from. A photon from an antimatter star is identical to one from a matter star. So even if an anti-galaxy existed, we might not know, unless we saw its edge, unless we caught the flicker of boundary collisions. So far we haven't. But we're watching. Now shrink again, not in space, but in scale. Because there are theories that antimatter could reveal itself not in stars, but in subtler ways, in the spin of a muon, in the lifetime of a meson, in the silent choices of neutrinos. The muon G2 experiment at Fermilab has measured anomalies in the magnetic moment of muons, tiny differences from prediction. Some speculate these could hint at unknown particles, unknown forces, perhaps even a deeper kind of antimatter, because the standard model of physics, as successful as it is, leaves things out. It doesn't explain dark matter, it doesn't explain why neutrinos have mass, it doesn't explain the asymmetry between matter and antimatter. So physicists build new models, supersymmetry, extra dimensions, mirror worlds. In some of these models, for every particle, there exists not only an antiparticle, but a superpartner, a shadow of the shadow, a twin beyond the twin. If these particles exist, they may help explain the missing pieces. They may be stable, invisible, and widespread. In other words, dark matter. So antimatter becomes more than a twin. It becomes a path. Let's return to Earth for a moment. One of the most intriguing uses of antimatter isn't cosmic at all. It's practical, quiet, almost domestic. In materials science, positron annihilation spectroscopy is used to study the internal structure of solids. Injecting positrons into materials can reveal voids, defects, and dislocations. The positrons annihilate with electrons in the material, and the energy they release tells us about the surrounding atomic environment. This technique is used in metallurgy, semiconductor research, and even archaeology. Antimatter, used to read the grain of a stone, the layers of an artifact, the flaws in a microchip, not with force, but with disappearance. There's a quiet poetry in that. Then there's the future. If we ever build interstellar spacecraft, antimatter might be the fuel. A single gram could, in theory, propel a ship a long way, far further than chemical rockets or even fusion drives. Some proposed engines use magnetic nozzles to direct the annihilation products, converting the energy into thrust. It wouldn't be easy. You'd need magnetic containment fields stronger than anything we currently use. You'd need shielding, cooling, and precise control. But the math works, and so the dream persists. Not because it's easy, but because it invites us to imagine ships powered not by fire, but by symmetry, by the meeting of opposites, by the erasure that leaves forward motion behind. Some even imagine using antimatter for terraforming, as a way to heat a frozen moon, or initiate a reaction in a distant planet's atmosphere, just micrograms, enough to spark change. This is not near term, but it is not impossible. And again, it makes us ask, what is a dangerous substance? Is it one that destroys, or one that can be misunderstood? Because antimatter, like fire, like gravity, like time itself, is neither good nor evil. It simply is. And it does what it does perfectly. That perfection is what makes it powerful and humbling. Let's pause here before we dive into stranger waters. We've seen that antimatter behaves like matter, follows the same rules, but it also reveals the exceptions, the places where nature shrugs slightly. Its annihilation gives us energy. Its absence gives us questions. Its behaviour might point us to a larger theory still unfolding. And in all of this, we begin to see a pattern. Antimatter doesn't just challenge physics, it asks better questions. Questions about identity, symmetry, time. And those questions, in the hands of careful dreamers, become tools. So let's go one layer further next, where antimatter and thought begin to blend, where possibility becomes not science fiction, but speculative physics, where we ask not only what antimatter is, but what it could have been. In the quietest corners of theoretical physics, where the chalk marks linger long after the thinkers leave the room, antimatter is still whispering. Not loudly, but insistently. It hints at questions we don't yet know how to phrase. Some physicists have proposed that antimatter might hold a different relationship to time itself, not just appearing to move backward in equations, but literally travelling in reverse. This idea stems from the strange symmetries found in the laws of physics: time reversal symmetry, charge conjugation, and parity inversion, C, P, and T. Flip all three, and the laws of physics don't mind. So what if, on some deep level, an antiparticle isn't just a mirror of a particle, but its opposite in time? When a positron appears, could it be an electron moving backward from a future collision? This isn't provable in a laboratory, not yet, but it emerges naturally from the mathematics, and it makes you wonder, if the arrow of time is born from entropy, from disorder increasing, then could antimatter reveal an order we're not built to perceive? Could it be that the universe does not have a single arrow but many, and that we, being made of matter, see only one? Antimatter might also reshape how we think about information. In quantum mechanics, every interaction is reversible in principle. Every particle collision, every wave function collapse, follows rules that could be run backward. But annihilation feels final. When a particle and its antiparticle meet, they become light. The mass is gone, the structure is gone, the identity is dissolved. Yet the energy remains, the momentum is preserved, the charge accounted for. Nothing is lost, just rearranged. This leads to deeper questions. If identity is reversible, if matter can become light and back again, then where is the dividing line? What defines the continuity of a thing? At what point is it no longer itself? These are not just questions for physicists. They echo in consciousness, in memory, in the nature of being. Antimatter doesn't answer them, but it points in their direction. In the realm of cosmology, some theorists suggest that the entire universe may have a twin, a mirrored cosmos, equal in mass, opposite in charge. A universe made entirely of antimatter expanding backward in time from the Big Bang. This is not just poetic metaphor. It's a hypothesis being explored mathematically. Such a mirror universe would obey the same physical laws. It would have stars, galaxies, perhaps even life. But it would be made of antimatter, and to its inhabitants, we would be the reversed ones. From our perspective, it runs backward. From theirs, we do. And yet, neither is wrong. This idea preserves symmetry on the larger scale. It restores the balance that the observable universe seems to have broken. And it makes the asymmetry we see here, the lack of antimatter, not a flaw, but part of a larger structure. Two halves of a whole, two arrows of time pointing away from a shared origin. Speculative, certainly. But speculation is where some of physics's greatest revolutions begin. Dirac once speculated about a positive electron, and the positron was found. Symmetry has always been a guide. A map not to what we know, but to what we should expect to find. And when we don't find it, when the symmetry breaks, that's when things get interesting. Because that break, that deviation, is where the story lives. At a more grounded scale, scientists are investigating whether antimatter might interact differently with dark energy, the mysterious force driving the acceleration of the universe's expansion. Could the repulsive force we attribute to dark energy be, in part, a shadow of antimatter's influence? No evidence yet. But the possibility is being modelled, explored, and if even part of that connection proves true, it could alter how we see cosmic structure, fate, and the long arc of expansion. It could explain not only why antimatter vanished from our corner of the universe, but why everything continues to drift apart. Meanwhile, quantum gravity, the attempt to unite general relativity with quantum mechanics, has its own puzzles. Some approaches, like loop quantum gravity or string theory, suggest that space-time itself is quantized, that at the smaller scales, distance and time are not continuous, but granular. In these frameworks, antimatter might emerge not just as a particle, but as a reflection across the structure of space-time itself. A fold in the weave, a twist in the thread. Again, we are far from proof, but these questions are not idle. They drive the designs of future experiments, future telescopes, future equations. Because antimatter isn't a footnote in the story of the universe. It might be half the manuscript. If all this feels like dreaming, it is. But science dreams in equations, in measurements, in the whispering trace of a particle that lived for less than a blink, but changed the conversation forever. And that's what antimatter does. It invites us not only to ask, but to wonder well. To believe that the mirror, however distant, might one day speak. And in doing so, it teaches us something deeply human. That opposites are not enemies. They are the shape of thought, the form of questions, the path we take in the dark toward what might be real. Science doesn't begin with certainty. It begins with a question, a tremor of curiosity, a shadow on the wall that doesn't quite belong. And the story of antimatter begins, fittingly, with such a shadow. In the 1920s, quantum mechanics was beginning to reshape how we understood the universe. Electrons, photons, wave functions. Suddenly the world of the very small was becoming legible, though never quite tame. Enter Paul Dirac. Quiet, brilliant, a man of few words, but of long thoughts. In 1928, Dirac sought to reconcile quantum mechanics with Einstein's theory of special relativity. He wanted an equation that could describe the behavior of electrons at high speeds. He found it. It was elegant, powerful, and strange. Dirac's equation worked. It predicted the known properties of the electron, including its spin. But it also predicted something else. A mirror solution. A particle with the same mass as the electron but with opposite charge. At first, Dirac didn't believe this particle could be real. He called it a hole, a vacancy in a sea of negative energy, an abstraction. But the math didn't go away. It waited. And in 1932, the waiting ended. Carl Anderson, studying cosmic rays with a cloud chamber, observed a curious track, a particle that curved like an electron, but in the opposite direction. He had discovered the positron, the first antiparticle. Suddenly, Dirac's abstraction had a name, a mass, a place in the world. It was real. And with that, antimatter stepped from theory into fact. The discovery of the positron cracked something open. If the electron had a twin, what about the proton? What about the neutron? By the mid-1950s, technology had caught up with imagination. Particle accelerators could now produce collisions energetic enough to create antiparticles artificially. In 1955, the antiproton was discovered at the Bevatron in Berkeley, California. Physicists Emilio Segre and Owen Chamberlain led the team. Their work confirmed that antimatter wasn't limited to light particles. The heaviest building blocks of the atom had shadows too. A year later came the antineutron. And slowly, piece by piece, the possibility of antimatter atoms emerged. If you could make an antiproton and a positron, you could make antihydrogen. And if you could make antihydrogen, why not antihelium? An anti-world? But even as the particles were found, the questions multiplied. Why is the universe made of matter? Where did all the antimatter go? In theory, the Big Bang should have produced equal amounts of matter and antimatter. And yet, all around us, we see only one side of the coin. Why? In the 1960s, a clue appeared. At the Brookhaven National Laboratory, James Cronin and Val Fitch observed something strange in the decay of neutral kaons. These particles and their antiparticles were not behaving as perfect mirror images. They had violated CP symmetry, the combined inversion of charge and spatial parity. This was huge. It meant that the universe did, in certain cases, treat matter and antimatter differently. It offered a mechanism, a tiny asymmetry that, scaled across the cosmos, might explain the dominance of matter. For this discovery, Cronin and Fitch were awarded the Nobel Prize, and the field shifted again. In parallel, new detectors and new techniques emerged. Physicists began capturing cosmic rays, looking for naturally occurring antiparticles from space. The idea of antimatter wasn't just theoretical or lab-bound anymore. It became part of astrophysics, cosmology, even planetary science. Antiprotons were detected in cosmic rays. Positrons too, not in large amounts, but enough to prove that nature itself was still producing antimatter. Meanwhile, particle colliders like CERN's ELA and later the LHC pushed energies higher and higher. New generations of antiparticles were created and studied: antimuons, anti-Tor particles, anti-quarks in their many flavours. Each one revealed another layer of symmetry, and sometimes its cracks. In 1995, a major milestone. CERN scientists created the first atoms of antihydrogen, real atoms, not just antiparticles but structured neutral antimatter. They used traps made of magnetic fields, shaped like invisible cages. These antihydrogen atoms lived only briefly, milliseconds at first, but they lived. Later experiments extended their lifetimes. In 2011, antihydrogen was trapped for over 15 minutes. That opened the door to testing whether antimatter obeys the same physical laws as matter. Spectral analysis, gravitational behaviour, magnetic moment. All questions now within reach. And the answer so far? Symmetry holds. But we keep testing. Because if one property, even one, deviates, it could unlock everything. Across the decades, as the search continued, antimatter began to move from the lab into life. PET scans, invented in the 1970s, use positron-emitting isotopes to visualize the inner workings of the human body. In engineering and material science, positron annihilation reveals microscopic cracks and voids. Antimatter, once a ghost, had become a tool, not just a threat, not just a riddle, a presence, measured, directed, useful, and still the most dangerous substance known. 1 gram, properly confined and released, could yield as much energy as a nuclear bomb. Yet, here it is, quietly helping doctors read minds and hearts. This tension between annihilation and insight, danger and discovery, defines the history of antimatter, a story of symmetry, of duality, of asking what the mirror shows when we dare to look. From Dirac's equation to Anderson's cloud chamber, from particle accelerators to PET machines, we have chased the shadow, and in doing so, found new kinds of light. But the timeline is not finished, because there are more particles to test, more symmetries to question, and still that aching mystery. Where did the rest of it go? We don't know. Yet. The story continues not in leaps, but in layers. After the creation of antihydrogen, the scientific community moved toward precision, testing not only if antimatter exists, we knew that, but whether it behaves exactly like matter. And so, the Alpha experiment at CERN began refining its traps. Cooling techniques improved. Detection grew more sensitive. By the late 2010s, physicists were comparing the spectral lines of hydrogen and antihydrogen with unprecedented accuracy, measuring transitions, looking for any tiny deviation that might hint at a fundamental difference. None found, at least not yet. This is science at its quietest, not revelation, calibration. Thousands of hours spent waiting for a handful of atoms to whisper their secrets. But the whispers are worth it, because even one crack in symmetry could mean new physics, a window into forces we haven't yet named, laws that lie beyond the standard model. Meanwhile, other experiments explored gravity. Would antimatter fall the same way as matter? Classical physics says yes, general relativity says yes, but quantum gravity? We don't know, and the only way to find out is to drop it. Literally. Alpha, G, and G bar, both at CERN, are designed to test this. They trap antihydrogen and measure how it behaves in Earth's gravitational field. These experiments are ongoing, technically demanding. The The particles must be cold, slow, isolated, but the data is coming. And whatever it reveals, we will learn something fundamental about how the universe holds its shape. Outside the lab, interest in antimatter continued to evolve. In 2016, the Alpha Magnetic Spectrometer, AMS-02, aboard the International Space Station, reported unexpected positron excesses in cosmic rays. Could this be the signature of dark matter annihilating, or of pulsars, or of something stranger, regions of the universe where antimatter still lingers? The data raised more questions than answers, but it proved something important. Space is still speaking, and we must keep listening. Meanwhile, theories continue to unfurl. Some suggest that matter and antimatter were separated by inflation, the rapid expansion that occurred fractions of a second after the Big Bang. Others propose that dark matter itself could be made of stable antiparticles from a hidden sector. A mirror world with its own versions of atoms and forces. These ideas are speculative, yes, but they shape how we design detectors, how we interpret results, how we imagine what might be just out of reach. In physics, even the unconfirmed changes the map. Today, the study of antimatter bridges the smallest scales and the largest questions. In laboratories, we trap antiatoms. In orbit, we scan for cosmic ghosts. In equations, we explore the possibility of universes beyond our own. Antimatter is no longer just an idea. It is an instrument, a lens through which we study the deepest laws. It reminds us that the universe is not flat, not finished, but folded, layered, symmetrical, but not quite. And perhaps that is the most poetic part of all, that every step we take toward understanding antimatter is a step inward, into the architecture of balance, into the grammar of contrast. We began with a question, a strange solution in a strange equation. Now we have traps that hold silence, machines that listen to atoms that should not exist. And through all of it, one mystery remains. Why this world and not its opposite? Why matter and not antimatter? We don't know. But the more we ask, the better the questions become, and perhaps, someday, they will lead us to the answer that has been here all along, not in what we see, but in what has vanished. Some ideas in physics do not shout, they linger. They return not with urgency, but with weight, like a thought you almost had in a dream, brushing just beneath the surface of waking. Antimatter is one of those thoughts. It is real, measurable, captured in labs and equations. But it is also conceptual, symbolic, heavy with meaning. Because what does it mean that for everything, every particle, every corner of matter, we can write a mirror? Not just a flipped version, but something exact in mass, opposite in charge, identical in behaviour, until it touches its counterpart. Then they vanish. Matter plus antimatter equals energy. Pure, perfect transformation. And that transformation is not violent in theory. It is elegant, balanced. But to us, who live in a world made only of matter, it feels like a kind of ghost story, because we are here, and it is not. Imagine walking through a universe made entirely of antimatter. Nothing would look different. Planets would orbit stars, trees might grow, light would shine just the same. You wouldn't know unless you touched something made of matter. Then the illusion would burn away. That raises an old question, dressed now in new physics. If two realities are indistinguishable in every way but cannot coexist, which one is real? Or are both? This, of course, echoes old metaphysical questions. What is identity, if something can have a twin so perfect it behaves the same? What is being, if it can be undone by its mirror? What is presence, if the universe chose one version of itself and not the other? Is that choice random? Is it necessity? Or something deeper? In classical logic, opposites cancel. But in the universe, opposites create. Matter and antimatter don't just annihilate. They release. They give back to the field that made them, as if their separation was temporary all along. And that leads to the deeper mystery. Why is there anything at all? Why didn't all the matter and antimatter in the early universe cancel each other out entirely? Why this sliver, this leftover of matter that built stars, galaxies, us? The laws of physics don't offer a satisfying answer yet. They show the imbalance, they measure it, but they do not explain it. So philosophers step in, gently, and ask again, was this universe a coin toss, or was the outcome always inevitable? And if matter had lost, would we be asking the same questions mirrored? Would the anti-version of this very reflection be humming its own inquiry somewhere in the unreachable vast? Antimatter doesn't just reveal the universe's workings, it reveals its preferences. We thought the laws of physics were symmetrical, but they're not entirely. Certain particles decay slightly differently than their antiparticles. A subtle tilt, a slippage. Nature, it seems, has a bias, not loud, but meaningful. It's like finding a fingerprint in an otherwise perfect mirror, and that imperfection is what allowed anything, us, to remain. To many physicists, this is the most haunting fact of all, that we owe our existence not to balance, but to imbalance. We live in the leftovers, in the 1 in a billion particles that didn't find a twin to cancel them out. Every atom in your body is the survivor of an ancient annihilation. You are what remained. And if just one rule had been different by a fraction, nothing would have remained at all. No stars, no time, no questions. So we ask, is antimatter a real thing? Or is it a memory? A reflection of what could have been? A reminder that the universe almost chose differently? There is something poetic about that. That a scientific reality, tested and trapped and measured, also serves as a kind of cosmic metaphor. That for everything there was once an echo, and for all we understand, we do not yet understand why it fell silent. Let's go further. What if antimatter is not just a particle, but a property of the fabric of reality? Some theories propose that antimatter might be linked to time reversal, that in certain formulations, an antiparticle is simply a particle moving backward through time. The math allows it. In Richard Feynman's diagrams, electrons and positrons are drawn as paths bending in opposite temporal directions. So perhaps when a positron appears, it's not emerging from nothing, it's returning. Maybe antimatter isn't the opposite of matter at all. Maybe it is matter's reflection in a temporal mirror. Maybe the universe allows for 2 directions, and we're only seeing one. Of course, this leads to wild implications. If antimatter moves through time differently, could it remember differently? Could a reality dominated by antimatter think differently? We don't know. We may never know. But even to pose the question is to step into a kind of philosophical space that physics often resists. A space of maybe. A space of what if. And yet physicists do ask, because antimatter brings them to the edge of what can be observed. It is stable, predictable, and profoundly missing. That paradox forces us to confront other dualities, symmetry and asymmetry, order and entropy, cause and effect. The laws of physics, elegant though they are, leave much unexplained. Why is the universe comprehensible? Why does it permit structure? Why should anything exist at all, when non-existence is so much easier? Maybe antimatter is the universe's built-in reminder that what we see is not the whole, that what vanishes still matters, that the parts that cancel, that subtract, that disappear, are still part of the story. Maybe it's not about survival, but about what's possible, what could have been, what still might be. That's where we'll continue next, into the more speculative corners, the multiverses, the alternate timelines, the mirrored cosmologies, because antimatter doesn't just belong to physics textbooks, it belongs to thought, to wonder, to the long, slow unfolding of a question we can feel more than answer. In certain corners of cosmology, there are whispers of a mirrored universe, not metaphorical, literal. A second cosmos, made entirely of antimatter, expanding not forward, but backward in time from the Big Bang. Identical in law, opposite in direction. This isn't fantasy, it's a hypothesis under study. A proposal that would preserve the universe's total symmetry, accounting for our matter-filled world by pairing it with an antimatter twin. From our point of view, that universe is running in reverse. From its point of view we are, and neither is wrong. Both obey the same equations, both began in fire, both unfold according to logic, but their arrows point away from each other, like a breath in and a breath out. Imagine a particle created at the moment of the Big Bang. One half travels forward in time. It becomes part of us. Atoms, galaxies, thoughts. The other half travels backward. It never reaches us, but it echoes us. It balances us. Not in location, but in logic. And so the Big Bang becomes not a beginning, but a meeting point. A point of highest order, from which two timelines ripple outward, never to touch again. Unless they loop, unless time is not a line at all. These are not conclusions, they are invitations. To ask whether time flows, or whether we do. To ask if the universe prefers one direction, or if we simply exist on a slope and mistake the tilt for truth. Antimatter raises these questions not because it is strange, but because it is symmetrical. And the symmetry reminds us that our version of reality is not the only one that could make sense. It just happens to be the one that remained. In speculative physics, the mind stretches further. Some posit that dark matter is not matter at all, but a form of antimatter that doesn't annihilate because it exists in a separate sector. Invisible, weakly interacting, but vast. A hidden world, a second standard model with its own particles, its own forces, its own rules. If so, then antimatter is not gone, it is simply elsewhere. Which begs a quieter question. What does elsewhere mean when it comes to the structure of reality? Is it distance or dimension? Other theories imagine mirror worlds, not parallel universes exactly, but reflected systems embedded in our own. They interact only via gravity. Their stars do not shine for us. Their atoms do not touch ours, but they exist alongside us like shadows with mass. And perhaps, under certain extreme conditions, a neutron decaying just right, or a high-energy collision, we might glimpse the seam between realities. Not a portal, just a flicker. A place where the mirror fogs, and a question becomes a possibility. These ideas, wild as they are not fantasy. They come from equations, from measurements, from the gaps between predictions and results. Physics lives in those gaps. That's where the next story begins. Even consciousness has not escaped the touch of antimatter, at least as metaphor. If matter is presence, and antimatter is absence that behaves as presence, what does that suggest about the self, about memory, about dreams? We're used to thinking in binaries, something or nothing, yes or no, on or off, but antimatter teaches us that opposites can be equivalent, that two things can cancel and still leave something behind. A photon, a flash, a trace. So maybe thought works like that too. Maybe the stories we forget echo softly, as energy in the background. Maybe every decision not taken, the anti-version of our lives, has its own kind of existence. Not material, but possible, like antimatter, not gone, just unchosen. This too has ancient echoes. The Tao, in Chinese philosophy, speaks of balance, not as stasis, but as the ongoing dance between opposites. Yin and yang, presence and absence, being and non-being. Not enemies, but twins. The Greeks too imagined a cosmos of opposites. Fire and water, earth and air, love and strife. Always returning to balance, always seeking the symmetry beneath the chaos. And so, When modern physics speaks of antimatter, it does not speak in isolation. It joins a chorus older than science, a human longing to understand duality, to explain the mirror, to name the ghost. We end with this. If the universe had chosen differently, if antimatter had won, nothing would be different. The stars would still burn. The rules would still hold. Minds might still wander. But we would not be here. And that is perhaps the most humbling truth of all. That reality did not have to include us, but it did. And in that brief, fragile accident, we were given the chance to look back, to measure the echo, to ask the question, not just what is antimatter, but what does it mean that it isn't here? And why, even now, we can't stop looking for it. We tend to think of antimatter as distant, something for particle colliders, space telescopes, or maybe a sci-fi villain with glowing red eyes. But in truth, it's already here. It's part of your life. Maybe not in grams or buckets or containment fields, but in sparks, in scans, in the gentle hum of modern tools that quietly rely on it. Antimatter isn't just in the cosmos, it's in the hospital down the street. The most common encounter happens in medicine. If you've ever had a PET scan, a positron emission tomography scan, then antimatter has moved through your body. It's an elegant trick. Doctors inject a tiny amount of a radioactive substance into your bloodstream. That substance emits positrons, the antiparticles of electrons. When those positrons meet electrons in your body, they annihilate. And that annihilation produces gamma rays. Those rays are detected by a ring of sensors around you, allowing doctors to build a detailed image of what's happening inside. Metabolism, blood flow, chemical activity. It's precise, gentle, and life-saving, all made possible by annihilation. It's strange to think about, isn't it? That the most dangerous substance in the universe is being used calmly to diagnose heart disease and cancer. There's something quietly beautiful about that. That destruction, properly channeled, becomes clarity. That opposites, when guided carefully, can tell the truth. Antimatter also helps engineers. In materials science, positron annihilation spectroscopy is used to detect tiny voids and defects in materials. When positrons are introduced into a substance, they behave differently depending on the local structure. By analysing how and when they annihilate, researchers can understand the microstructure of metals, polymers, semiconductors, things too small for even microscopes to see. It's like echolocation, but with disappearing particles, and again, it's subtle, controlled, useful. We don't walk through clouds of antimatter in daily life. The universe doesn't allow that. But we walk through the consequences of its existence. We live inside a world shaped by its absence, and that absence is informative. When you light a candle, the flame dances because of electrons, but the emptiness around the flame, the space that keeps the fire from spreading, is antimatter's silence. When you drop a stone, it falls because gravity pulls on its mass. But mass, in quantum terms, is a kind of tension between particles and fields, between something and its potential opposite. That potential is always there. We see only one side, but physics remembers both. Even in language, the idea of antimatter has crept in. We talk about polar opposites, about two sides of the same coin. We use mirrors as metaphors for truth, deception, duality. We describe people as being someone's perfect opposite. Same energy, reversed. This isn't science exactly, but it's telling. The human brain is wired to understand contrast. Not in spite of our survival, but because of it. We notice light because we know dark. We feel joy because we remember pain. We value peace because we've touched chaos. And so, when physics tells us there's a twin for every particle, our minds understand, almost instinctively, that this is not just math. It's meaning. Antimatter lives at the intersection of science and poetry. It's a subject studied with magnets and vacuum traps, but also whispered about in speculative fiction, spiritual metaphors and philosophical riddles. We use it to build plots, stories, dilemmas. In fiction, it powers warp drives. It threatens worlds. It serves as a test of what happens when reality breaks its own rules. In culture, antimatter has become a symbol for balance and danger, creation and undoing. In Dan Brown's Angels and Demons, a canister of antimatter becomes the centre of a suspense thriller set against the backdrop of Vatican City. In Star Trek, antimatter powers the warp core of the Enterprise. In video games, it's often a weapon. In comics, a force of ultimate danger. We rarely use it to talk about healing, though in reality that's what we've done with it most. But maybe that's the point. Antimatter occupies a strange space in the imagination. It's not exactly evil, but it is reversing. It's undoing. A thing that erases what is. And humans, biologically, don't like that idea. We are builders, makers, survivors, so anything that undoes feels like a threat, even when it isn't, even when it's simply part of how the universe keeps score. Yet, on some level, we understand. We know that destruction and creation are linked, that the forest burns and new seeds sprout, that stars collapse and heavier elements form, that even in death there is recycling, atoms return to the field to be reused. Antimatter is that principle, made particle, a reminder that opposites are not just real, they are required. In daily life, we rarely think about this. You go to work, you make dinner, you scroll past headlines, and yet, behind it all, behind the hum of electricity and the glow of screens and the molecules in your lungs, there is a universe that almost didn't choose you, and chose you anyway, because for reasons still unknown, matter won. Antimatter blinked. And in that blinking, everything we know became possible. That knowledge doesn't make traffic jams or heartbreak easier, but maybe it makes them more wondrous, because they too are artifacts of improbable survival. They are echoes of particles that didn't vanish. They are what's left when the mirror shatters and one side walks away. There's a strange kind of comfort in realizing that something so alien, so mathematically pure, so physically destructive, has become part of our normal world. We often think of antimatter as exotic, dangerous, unreachable, but what it really reveals is something much simpler. We live with mystery, constantly, quietly. Antimatter is just one of its names. Take time, for example, not just in the abstract cosmic sense, but in your own experience. Why does it move the way it does? Why does the past feel solid, the present fleeting, the future uncertain? Why do moments stretch or vanish depending on mood, memory or meaning? Antimatter doesn't answer these questions, but it reflects them, because it suggests that everything, even direction, is conditional, that what feels fixed may not be, that what we think is normal is simply what remained. Children, for instance, have no concept of antimatter, but they intuit duality. They understand opposite. They create mirrored worlds in play, upside-down days, backward speak, left is right worlds. It's not nonsense, it's practice. A way of understanding that the world could be otherwise, that the rules they live by are rules, not laws, that for every direction there might be another one, hidden or forbidden, or simply not chosen. And culturally we've leaned into this. The idea of the other side appears in folklore across the world. In Celtic myth, the other world is a mirror of our own, reachable through fog or forest. In Japanese Shinto, there is the concept of the yomi, a shadow realm not of evil, but of stillness. In ancient Egyptian cosmology, the underworld was not hell, but a place where the soul encountered its double. Antimatter fits into this lineage, not as belief, but as metaphor. It is the scientific name for the ancient idea that every presence casts a reflection, that every something carries its nothing. Even in emotion, we see this echo. Joy is more vibrant because sorrow exists. Grief is shaped by love's outline. Laughter lives beside the memory of silence. We are constantly experiencing our own anti-feelings, those opposites that define the edge of the real. Not negations, not erasures, just mirrors. In spiritual language, this shows up too. The yin to yang, the dark night of the soul, the void that gives rise to form. Even non-duality, the idea that opposites are not truly separate, can be seen through the lens of matter and antimatter. Two forces made of the same essence, shaped differently, behaving identically until they meet. Then, transformation. In sleep, perhaps, we brush closest to the edge. Dreams are often symmetrical to waking life, but skewed. Reversed logic, bent rules, familiar people doing unfamiliar things. It's not science, but there is a strange symmetry there too. A sense that dreams are a kind of antimatter to waking thought. Unstable, beautiful, transformative. And when you wake, they vanish, not with violence, but with a light. And maybe, in that small metaphor, we find the human layer of antimatter, that we are always creating things that can't coexist. Dreams and duties, desire and doubt, hope and history, we balance them. We try not to let them touch, because we know instinctively that when opposites collide, something ends, but also something begins. This is what antimatter reminds us. Not that destruction is inevitable, but that it is necessary. Not that opposites are dangerous, but that they are meaningful. That the universe is not random, it is deliberate, even in its contradictions. So the next time you hear the word antimatter, don't think of space weapons or doomsday traps. Think of what's quietly humming inside your body when a PET scan lights up your heart. Think of the electrons that survived a cosmic coin toss and built your hands. Think of the questions you carry about meaning, about time, about love, and how they too exist alongside something opposite, something unspoken, but not unreal. And in that space maybe wonder softens, not as a puzzle to be solved, but as a rhythm to be followed, a dance of symmetry and silence, a balance not meant to be resolved, but simply held. Antimatter is not just physics, it is the universe's way of whispering. There was another version. You were not the only possibility, but you're the one that happened. Imagine this, a ship drifting silently through interstellar space. No fuel lines, no turbines, no nuclear cores. Its engines hum with a quiet, endless pulse. The source of that energy? A few milligrams of antimatter held in magnetic suspension, never touching the walls of its chamber. Perfect annihilation. Pure propulsion. The dream of many science fiction authors, and increasingly a subject of real-world speculation. What if we could harness the most efficient energy release known to physics? What if the weapon of unmaking became the engine of exploration? Antimatter, when it meets its counterpart, transforms its entire mass into energy. No leftover nuclei, no smouldering debris, just light, heat, motion. Einstein's equation in its most literal form. That makes it not only the most dangerous substance we've ever theorized, but also the most efficient. And in that contradiction lies the beginning of countless what-ifs. The first one is technological. What if we could produce antimatter in large quantities? Right now, the process is agonizingly slow. It takes billions of dollars worth of particle accelerators to generate just a few nanograms. We have, quite literally, produced less antimatter in a century than the mass of a single mosquito. But that's today. What about tomorrow? Suppose we cracked the problem. Suppose we learned to make it faster, cheaper, safer. Suddenly a world of new possibilities unfolds. Interstellar travel. Deep space probes that never run out of fuel. Emergency energy cells the size of aspirin tablets capable of powering cities. The smallest flare of antimatter could lift a ship beyond gravity's grip. A controlled stream could drive it between stars, but even then the challenge would remain containment. Antimatter can't touch matter, not even the walls of a fuel tank. That means storage has to be perfect. Magnetic fields, vacuum traps, perhaps even quantum cages that deflect antiparticles from existence itself. One breach, one failure in the system, and all that potential becomes catastrophe. Still, science fiction embraces the risk. In stories, antimatter is not just a battery, it's a key. A way to fold space, warp time, open gates to elsewhere. In the Star Trek universe, it fuels the warp core. In Doctor Who, it leaks from collapsed universes. In video games and novels, it's often misunderstood, weaponized, worshipped. The substance that can either end all things or begin them anew. What if it could also unlock time? Some theories, including interpretations of Feynman diagrams, suggest that antimatter might be time-reversed matter, not metaphorically but mathematically. In this view, a positron is just an electron moving backward through time. It looks like a particle, behaves like a particle, but in a different frame of reference, it's retracing a path we haven't seen yet. If that's true, what would it mean to interact with antimatter at scale? Could we, by manipulating its motion, influence the direction of causality? Could we send signals not only across space, but back through time? This idea is often dismissed as fanciful. Time, in thermodynamics, flows with entropy. There's no known way to reverse it. But antimatter already challenges other symmetries. It violates expectations. It hints. And so fiction picks up the thread. What if a future civilization learned to use antimatter not to propel ships, but to navigate timelines? What if each antimatter reaction weren't just an energy release, but a point of divergence, a place where alternate realities split off? What if, each time a particle and its antiparticle met and vanished, something else emerged on the other side? Parallel worlds, quantum branches, mirror histories. In some interpretations of quantum mechanics, like the many worlds theory, every quantum event spawns a new universe. Antimatter might be the hinge, the mechanism by which these branches unfold. A positron doesn't simply go back in time. It goes sideways, into the version of reality that could have happened, but didn't. What if we could follow it? Would we find worlds where the Big Bang tilted the other way? Where antimatter won the cosmic battle, and matter is the missing side? In those worlds, stars still burn. Life may still evolve. But everything we know, chemistry, biology, sensation, would be flipped. Would it feel different? Would it still be life if all its building blocks were reversed? There's no clear answer, but it's one of the oldest tropes in science fiction, the antimatter universe. A reality where everything is familiar and yet entirely not. Like a dream version of your own home, where the hallways bend slightly wrong and your reflection doesn't blink. Sometimes, in stories, characters cross into that world. Sometimes they meet their counterparts. Sometimes they destroy each other. But sometimes, rarely, they learn. What would it feel like to meet the antimatter version of yourself? Not evil, not opposite, just inverse. Same memories, same fears. But a body made of different particles, a mind running on reversed currents. Would you recognize them? Would they recognize you? Would you cancel each other out? Or would something new emerge from the meeting? Antimatter invites these questions not because it wants to. It simply is the question. A question embedded in the structure of physics. A question about what is necessary and what was optional. It's not just a theoretical tool. It's a narrative device. It shows up when science needs drama, when writers want stakes, when thinkers want symmetry to shatter, and yet, underneath the fiction, there is truth. We are living in the outcome of an ancient fork in the road, a coin toss where matter stayed and antimatter slipped away. That doesn't just make for a good plot twist, It makes for a real unresolved puzzle, because we don't know where it went, or why it lost. Maybe it didn't lose. Maybe it's just elsewhere. Maybe in some branch of the universe antimatter thrives. Maybe that's what dark matter is. Not unseen mass, but unfelt symmetry. Not invisible particles, but lost consequences. And what if we could talk to it? What if we could build not just detectors, but interfaces? Devices that interpret the echoes of a shadow world, its gravitational pull, its tiny breaches into our own. Messages not in sound or light, but in probability, in entropy, in subtle violations of symmetry that hint at conversation we haven't yet learned how to hear. It sounds like science fiction. But once, so did antimatter itself. The idea that there could be a particle with the same mass but the opposite charge, purely a product of mathematics, was fantasy, a mirror world on paper, until it wasn't. Until it curved the wrong way in a cloud chamber and changed everything. Perhaps, just perhaps, the next mirror will do the same. Imagine a universe where antimatter didn't vanish, where the early cosmos found perfect balance, every particle paired with its twin, dancing in symmetry across expanding space. What would that world be? Would it collapse under its own precision? Matter and antimatter meeting, cancelling, disappearing until nothing remained but silence? Or would it learn to separate, to sustain pockets of matter and antimatter in vast cosmic chambers, held apart by magnetic borders we cannot see? Some physicists wonder, could there be entire galaxies made of antimatter? Not just scattered particles, but structured worlds, anti-stars, anti-planets, perhaps even anti-life. If they exist, they'd be almost impossible to detect unless they came close, because the moment they touched our matter-based universe, the result would be annihilation. A burst of gamma rays, a flare that says, here was something, now it is gone. Some gamma ray bursts observed in deep space are so intense, so sudden, they've been speculated to arise from just such collisions. Antimatter and matter drifting unknowingly into each other after billions of years apart. A cosmic reunion, paid in light. But there's another possibility. What if these antimatter regions aren't out there, but nearby? What if they're right next to us, not in space, but in possibility? Quantum physics allows particles to exist in superpositions, states of being and not being until measured. What if antimatter is not elsewhere, but part of that hidden layer? A twin world stacked not beside us, but through us. One interpretation of quantum mechanics, called the transactional interpretation, treats interactions between particles as negotiations across time. A particle offers a way forward, its counterpart confirms it backward. A handshake across the temporal divide. What if antimatter is that handshake made real? What if every time a particle appears, its anti-self whispers from the other side, sealing the deal? That would mean the universe is constantly reaching into itself, folding futures and pasts into the present. It would mean that causality is not a one-way street, but a bridge crossed from both ends. Now imagine we learn to influence that handshake. What would time become? Would we build loops, messages sent back to stop the sending? Would we walk paradoxes like paths, changing the past, only to erase the version of ourselves that wanted to change it? In fiction, this is where antimatter shines brightest. It's the wild card, the explanation that lets characters break the rules. The antimatter reactor goes unstable, and suddenly the laws of physics unravel. Space folds, a timeline collapses, a new world rises. But what if these stories are less about breaking rules, and more about showing that the rules were never what we thought? Because antimatter isn't unnatural, it's not exotic, it's required. Its absence is what's strange, and that strangeness invites us to reframe everything. Take the idea of identity. What does it mean that you, sitting here, reading this, are made entirely of one type of particle? That your hands, your thoughts, your breath, all arise from a bias in the earliest moments of time. You're not inevitable. You're a version. Another version might have burned just as brightly, asked the same questions, lived the same joys, built from antimatter. You might not have noticed the difference, but with the universe. And if it didn't, what does that say about reality? Are we just consequences of initial conditions? Is life a rare accident of symmetry broken? Or is the universe flexible enough to support any pattern, so long as it's internally consistent? Antimatter says, yes. Yes to the mystery. Yes to the unknown. Yes to the terrifying freedom of a cosmos that permits opposites and doesn't always choose between them. In the deeper sense, it suggests a truth we often ignore, that we are here not because one path was better, but because it happened to unfold, and that maybe somewhere another version is unfolding still. There are darker versions too. What if humanity builds an antimatter engine and loses control? What if a reactor breach doesn't just destroy a city, but tears open the local fabric of space? In speculative physics, some theorists imagine that enough energy, compressed into a small enough region, could trigger vacuum decay, a collapse of the universe's underlying field. It's theoretical, remote, but it reminds us that antimatter, for all its potential, demands respect. Not fear, not rejection, but reverence. Because it holds a mirror up to our assumptions. It shows us what the universe could be without us. It lets us imagine what we would have become if the mirror had blinked the other way. So what if we could speak to that mirror? Not with words, but with equations, with energy, with controlled annihilation, a kind of communion across realities. Not a war, not an invasion, but a question asked gently. What were you? What are we? What could we be together? Fiction dreams of this. Books where matter and antimatter species meet and learn. Films where alternate timelines converge, not to collapse, but to evolve. In these stories, paradox isn't the end. It's the beginning of understanding. And perhaps that's the truest what if of all. What if antimatter doesn't answer our questions? What if it teaches us better ones? What if its role isn't to be fuel or threat or ghost, but invitation? A doorway made not of matter, but of meaning. So here we are, at the quiet edge of the strangest substance in the universe. Antimatter, the twin that never stayed, the shadow that never fully formed, the answer that asks more questions the longer you sit with it. We began with a whisper, a symmetrical echo in Dirac's equation, a theoretical negative waiting to be discovered. And we followed it, through cloud chambers, through particle accelerators, through positron scans and speculative universes. We watched as the mirror slowly revealed a story not just of particles but of preference, of a universe that, for reasons still unknown, chose one half of itself and let the other fall away. And yet it didn't fall far. It lingers in the map, in the sky, in the tools we build, in every annihilation event in a PET scan, in every question we ask about why there's something rather than nothing. Antimatter is not only science, it's a reflection, a reminder that symmetry is beautiful but not always sustained, that the laws of nature don't merely balance, they tilt. What does it mean to live in the residue of broken symmetry? To be made, down to your last atom, of the particles that didn't vanish? Maybe it means that existence is less about domination and more about accident. That you, like all things, are an outcome. A flicker of survival in a system that could have tilted the other way. We talk about antimatter as energy, as risk, as potential. But it's also a metaphor. A quiet one. One that reminds us of the beauty of opposites. Of balance almost reached. Of things that cancel each other out not in violence but in light. Maybe you've felt this elsewhere, in memory, in longing, in those quiet moments when you almost recall a dream, but it slips away before it forms. Maybe that's what antimatter is too. A cosmic dream remembered by equations, almost forgotten by reality. So what does it mean? Maybe not much. Or maybe everything. Maybe it means that every story, every breath, every star is both presence and absence. That we're not only what exists, but what was lost to make room for it. And maybe, in that, there's peace. Because the universe didn't need us, but it allowed us. And in return we notice, we ask, we wonder, we look for the twin that never came home. Not because we fear it, but because we want to understand what could have been. And that in the end is the quiet miracle. Not that antimatter vanished, but that something stayed. You, me, this moment, this soft echo where science becomes story and story becomes sleep. So, where are you now? What time is it? Where you are? Not on the clock, but inside, in your breath, in the rhythm of your thoughts. Has anything slowed? If this gave you peace, if it helped your mind wander a little farther out and a little deeper in, then thank you for staying. We've travelled far tonight. From the silent collisions of the early universe to the strange twins of particles and their opposites. From laboratories full of magnetic cages to the speculative landscapes of time loops and mirrored selves. And maybe, like antimatter, some of those thoughts will vanish when you wake. That's okay. Because not everything needs to remain to have mattered. Sometimes just brushing against an idea is enough. Sometimes the soft flicker of curiosity is the whole point. So thank you for letting this be your lullaby, your companion in the quiet, your thread of wonder in the dark. And if this kind of drifting through science and story feels like home, feel free to return, subscribe, share, or just remember that this place exists whenever you need it. Sleep well, fellow traveller, wherever you are and whenever you are. We'll see you in the next echo.